We have been discussing vector field A R that is related to magnetic field B R through curl equation. What we want to do in this lecture is develop an equation for the vector field A R directly in terms of the current density J of R. Something similar to Poisson's equation for V R, the electrostatic potential in terms of rho of R. And then if I can calculate A directly in an easier way than I calculate B and then take its curl to get B, that will be a good way of calculating B for a given current distribution. So, that is the motivation. To develop this equation, we start with the equation curl of A is B of R and take curl again on both sides. So, curl of A is equal to curl of B. But curl of B I know in terms of the current density, which is nothing but mu naught J of R. And the left hand side I know from vector identity is nothing but gradient of divergence of A minus Laplacian of vector A. By taking Laplacian of vector A, one means that you are taking Laplacian of each component of A, and this is equal to mu naught J of R. Now, recall from my earlier lectures that there is a freedom in choosing A, in that we can add a gradient to it, and therefore, I can choose A in such a way that divergence of A is 0. All right, if I do that, then I am left with the equation Laplacian of A is equal to minus mu naught J of R. That is the equation, Poisson's equation for vector field, if you like. Let us understand what it means. The equation we have is del square of A is equal to mu naught minus mu naught J of R, all right, under the condition that divergence of A is 0, and keep in mind that this is all for a steady state current. What it means is that each component del square A x is equal to minus mu naught J x R, del square A y at R is equal to minus mu naught J y at R, and finally, del square A z of R is equal to minus mu 0 J z of R. All these three equations are absolutely similar to this Poisson's equation phi of R is equal to minus rho of R over epsilon 0. All we are doing is 1 over epsilon 0 is being replaced by mu 0 and rho is being replaced by J x, phi is being replaced by A x and y and z component. Therefore, the equation has the same solution or similar solution as for the Poisson's equation. So, in free space, we already know the solution for the electrostatic potential. Oh, I have been using V r. So, I should be using V r. In free space, therefore, A x at r is going to be equal to mu 0 over 4 pi integral of J x r prime over r minus r prime dv prime. Similarly, a y at r is going to be mu naught over 4 pi integral j y at r prime over r minus r prime dv prime, and a similar equation for a z at r is equal to mu naught over 4 pi integral j z r prime over r minus r prime dv prime. To write it all together, what I have is then a vector at r is given as mu naught over 4 pi integral j vector r at r prime over r minus r prime dv prime. That is the equation for vector potential. Very similar to the equation for electrostatic potential, except that now I have 3 components, because this is a vector potential. Once I know the current density, I can calculate from this the vector potential, and taking its curl, I can always get my magnetic field. Let us now solve a few examples. As example 1, I am going to take current I going in a wire along the z axis. So, this is a well known example we have been solving so far, and I want to calculate for the vector potential directly. Let us write the current density for this. You see, current is going only at s equals 0, right, and I know by definition current density dot ds should be equal to I. Current density is going in the z direction, its magnitude is I, it is only at s equals 0, where the density becomes infinite, and to normalize I am going to do it divide by 2 pi s, and that is it. That is the current density. Let us check if this is correct. If I take this area across the wire, j dot ds gives me I delta s prime over 2 pi s prime, area is going to be 2 pi s prime ds prime z dot z, because area is in the z direction, integral 2 pi s prime cancels with 2 pi s prime, and integral over s prime gives me 1, and therefore, this is equal to I. So, I have got the correct current density. Let us then directly use this to calculate the vector potential. The vector potential A r is equal to mu naught over 4 pi integral j r prime over r minus r prime dv prime. Remember, this is a current carrying wire going from minus infinity to plus infinity. This is equal to mu naught over 4 pi integral I over 2 pi s prime, because it is at s prime, delta s prime, this is a vector in z direction, dv is going to be 2 pi s prime ds prime dz prime over. Since this is an infinite wire at any z, the answer for A is going to be the same. Therefore, I may as well calculate it at z equal to 0. So, this is going to be square root of s vector minus s prime vector square plus z prime square. Since s prime goes to 0, this becomes mu naught I over 4 pi in z direction, and you can see this 2 pi s prime and 2 pi s prime cancel. This delta s prime with delta s prime here gives me s prime equal to 0. So, I am left with integral minus infinity to infinity dz prime over the square root of s square plus z prime square. Let us do this integral. I do this integral by taking z prime equals s tangent theta, and this gives me mu naught I over 4 pi z integral s secant square theta d theta over s sec theta minus pi by 2 to pi by 2. This s cancels, and you can see this is the integral of secant theta d theta, which gives me log tangent theta plus secant theta, and that blows up in this case. So, I have to actually do this calculation by taking a long wire going from minus L to L, and then taking the limit L going to infinity, and that will give me the S dependence. So, let us do that properly. Therefore, I am going to write A at S z equal to 0, because now I am taking a long wire extending from minus L to L, and I am calculating A at z equal to 0. This is going to be equal to mu naught I over 4 pi integral minus L to L dz prime over square root of s square plus z prime square. This is in the z direction, which I can write as mu naught I over 4 pi times 2, because the integral is even in z prime. I can make it from 0 to L dz prime over square root of s square plus z prime square in the z direction. So, I get this to be equal to mu naught I over 2 pi in the z direction integral, again making a substitution, z prime equals s tangent theta. I get s secant square theta over s secant theta d theta. Tangent theta is going to vary from 0 to tan inverse L over s. All right. So, now let us do some cancellations again. S cancels, the secant theta square cancels here, and I get secant theta, and therefore, my answer comes out to be mu naught I over 2 pi in the z direction log of secant theta plus tangent theta 0 and tan inverse L over S, which I can simplify to at 0 tangent theta is 0, secant theta is 1. So, that gives me 0, and so this comes out to be A at S z equal to 0 comes out to be mu naught I over 2 pi in z direction log of tan inverse L over S, tangent of that gives me L over S plus square root of 1 plus L square over S square is the secant theta. For L going to infinity, this can be written as mu 0 I over 2 pi z log of L over S plus L over S again, because I can ignore that one. So, I will erase this and write this as 2L over S, which is equal to mu naught I over 2 pi z log of 2L minus mu naught I over 2 pi log of S z. This part goes to infinity as L goes to infinity. So, I can ignore this. I mean, this is just addition of infinity. So, the S dependence actually comes out to be A S. Z it does not depend on. So, I may write, may not write it, is equal to mu naught I over 2 pi log S in the Z direction. Indeed, the answer we had obtained earlier. Let us do one more example, and that is going to be that of a sheet of current for which we have already calculated magnetic field, and we also calculated A, but now we want to do it directly. this is x direction, this is y direction, and to remind yourself you may want to look up the lectures we have done earlier. This is z direction and this is carrying a surface current k, which is k in the y direction. So, this carries a surface current k is equal to k in the y direction. The current density can therefore be written as k. The area across which it is going is the y z plane. So, in the z plane it is confined to z equal to 0. So, I can write k delta z in the y direction. How do we check this? Let me take a cross section across which the current is flowing. So, if I do j r dot d s across this cross section, I am going to get, if this length is L, L d z k delta z y, which gives me, or y is the direction of area also. So, this gives me k L, which is the current indeed passing through length L of the sheet. So, our j is correct. Therefore, A, the vector potential A at any point r is going to be mu naught over 4 pi integral j r prime over r minus r prime d v prime, which is equal to mu naught over 4 pi integral k delta z prime in the y direction over r minus r prime d v prime. Now, let us see, this is a plane sheet. So, the answer should not really depend on which x, which y am I calculating it at, because it is invariant. It does not matter which x, which I am in, because in x y plane this is infinite extent. So, I may as well calculate A at x equal to 0, which will be the same as at any other x. It just makes my life little easy. Y equal to 0 and z, which will be equal to mu naught over 4 pi integral k delta z prime, it is in y direction, divided by r minus r prime. Since I am calculating it at x and y equal to 0, is going to be only x prime square plus y prime square plus z minus z prime square dx prime dy prime dz prime. That is the expression. Let us write this again. So, I am calculating, due to the sheet of charge which is carrying the surface current in direction y, we have calculated A 0, 0 it does not matter, any x y would be the same answer, at z is equal to mu naught over 4 pi integral k delta z prime, it is in y direction, dx prime dy prime dz prime over square root of x prime square plus y prime square plus z minus z prime square. Now, the integral over z prime, because of the delta z prime, gives me z prime equals 0, and therefore, this becomes equal to mu naught, k comes out, y direction comes out, it is a fixed direction, over 4 pi integral of dx prime dy prime over the square root of x prime square plus y prime square plus z square, both x and y going from 0 or minus infinity to plus infinity, minus infinity to plus infinity. I can make this integral very easy if I realize that this actually is an area integral. All right. So, I can convert this area integral into, in terms of the cylindrical coordinates or planar polar coordinates, whereby dx prime dy prime I can write as 2 pi s prime d s prime, x prime square plus y prime square is s prime square. So, instead of taking this dx prime dy prime, let me make it a different color like this, since this is an integral which is symmetric, I am actually taking this area and integrating over it. It is the same thing as long as I cover the entire area, and therefore, I can write this expression as equal to mu naught k y over 4 pi integral 0 to infinity 2 pi s prime d s prime over square root of s prime square plus z square. This 2 pi cancels with this, I get 2, and therefore, the expression becomes mu naught k y over 2 integral 0 to infinity s prime d s prime over s prime square plus z square square root. And this is very easy to calculate. Let us do that. So, we have gotten a at any point, but depends only on z, x y does not matter, is equal to mu naught k in y direction over 2 integral 0 to infinity s prime d s prime over square root of z square plus s prime square. Let us take z square plus s prime square to be some y square, so that y dy is equal to s prime d s prime. So, I get a z is equal to mu naught k over 2 y integral modulus of z to infinity y dy over y. This y cancels, and I end up getting mu naught k over 2 y at mod z and infinity. Again, at infinity, it is a constant which I will ignore, and therefore, the z dependence of A finally comes out to be A z is equal to mu naught k over 2 modulus z with a minus sign in the y direction. Indeed, the answer we had obtained earlier looking at B. So, you see, I have given you two examples where we can calculate A directly from a current distribution, and now I can take its curl and get my answer for B.